Hello, in this video, I'm going to have a quick look at some of the basic properties of indefinite integrals. And what I have here is a function which has just been created using lines. It's definitely a function. I could take any x coordinate here and pop up here and get a y coordinate and so on. It's not only a relation, it's also a function. So that's okay. But I've color coded it because you could imagine that this function is actually made up of three parts. This blue line would be one part of the function. Maybe it's y equals 2x plus 5, and then it might be y equals negative 2x plus 15, and then for, what do you reckon, something like it along the lines of y equals 2x minus or -4 or something like that. So, and it's just defined for particular intervals. So the important thing is that you can take one function and break it into smaller functions, and I've just color coded it in this instance to explain how a few of those functions. Now let me switch over to our textbook, and we'll have a look very quickly at some of the properties of definite integral. So just a reminder that a definite integral is an integral over a particular interval of x. It goes from A to B. Oops, my highlighting's not too flash there. From A to B. So here are 5 properties, and I wanted to briefly just have a look at them so that you've got a sense of where they're how they're utilized. So here, this basically says if I have a function multiplied by a constant value over a definite interval, then it's the same as working out the definite integral of the function and multiply the whole result by k. Okay, so if I go back to here, kind of imagine it like this. If this is f of x, then k f of x would be multiplying the output of the function by the same value k. And so effectively, every single value here would be stretched upwards, right? It's a vertical dilation where every single value will be stretched up. So if you can imagine, if we think of the definite integral as the area underneath the function, everything's stretched up. So it's probably little wonder that the resultant function, the integral of it, would be k times the area of f of x as a result. So hopefully that kind of makes sense. The second one is, it says here, the integral between b and a of f of x plus or minus g of x dx is the same as the definite integral of f of x plus or minus the integral of g of x. And I've got 3 parts of my function here. We could call this f, g, and h of x if you like. And you could see that if we again think of the integral, the definite integral, as being from, say, this point here. So point A, or maybe I'll go back to black, from point A to point B, then working out the area of underneath the entire curve would be the same as working out the area of this part plus the area of this part plus the area of this part. Okay, so it's just, there would be, I mean, if you look at this red line here, for example, the middle part, it's not defined over here and it's not defined over here. So ultimately, between A and B, it's only defined between this little section here. So you would only get this area. So again, intuitively, I hope that makes sense, that we can just split up a function here. The integral between A and A of a function is equal to 0. So again, if I just pick any random old point, if I go for a point A somewhere else, like here, and again, thinking about the integral as being the area underneath the curve, if that's A there, that's going to be an area with no width, right? And so if the area has no width, then the total area is going to be 0. So hopefully that makes sense to you. The next one here is that the integral between b and a of f of x is equal to negative the integral between a and b of f of x. And again, hopefully that kind of makes sense. If I look, we haven't looked at it formally, but if I look at the the fundamental theorem of calculus, you've sort of got the integral between b and a is equal to, of f of x dx is equal to big F of b minus big F of a. Okay, so if I take the negative outside of that, that would be F of a minus F of b. Okay, you can pause the video and have a look at that for yourself if you like, but that is true, what I've written. And that would be equal to the negative integral of from A to B that way of f of x dx. So hopefully that makes sense to you. The next one, or the last one I should say, is that the integral between b and a of f of x dx is equal to the integral from a to c of f of x, and then from c to b of f of x. This is what this means. This simply means that if I have, if I'm looking at the area under the function between a and b, like so, then that would be the area. Now, if we pick a middle point here, doesn't have to be the very middle, but somewhere in between a and b, like that point there, then all we're saying is that we've split up the area. So we've got this area here, and we've got this area here. So from a to b, assuming this is just one function, from a to b, we have, oops, that's a bit messy, f of x dx. Okay, and all we're saying is then let's just take the area from between a and c, so that's integral of f of x dx between a and c, and then we'll add the other area, which will, so we've just done that bit, and then we'll just do this bit. So that would be from c to b of f of x dx. So all we've done is we've really just sliced our function into two, with c being some sort of arbitrary point in between a and b. So hopefully that explains some of these properties of definite integrals. It's absolutely important that you are aware of these properties, because it will allow you to sort of simplify integral equations and solve them. And that's what I'll do in the next video. Okay, see you on the flip side.